Yeah, I've just been sent this by someone who sent it to a repair centre before, and they sent it back saying it couldn't be repaired, which was obviously rubbish. And the owner was pretty upset because when they took it back out of the unit to send it to me, I said just send the power unit in. They'd just cut the wires. Instead of unplugging all the wires, they just cut all the wires to the speakers, so they clearly they'd written it off, and they couldn't have the decency to reconnect everything they'd cut off, especially as they were connected by spade terminals anyway. So that's a bit strange, but engineers for you, eh? So it's a 120 230 volt 50-60 hertz universal input, and it's 400. How many watts is this? Let's turn it round so you can read it. It's a bass cab, I think. JBL 518S, Eon 518S. Yeah, so this was rated, looking at the data sheet, 500 watts continuous. I suppose is that RMS, who knows? Continuous watts, or 1000 peak. It's for an 18-inch subwoofer enclosure. Anyway, so I'll turn this over now. You can have a look at what's inside. I've never seen one of these before. It's the first time I'm seeing it too. And what have we got? So I've got the input Class D controller, Class D power amplifier, four very large output transistors, plus a thermistor, I think, capacitive decoupling for the power supply, a couple of chokes for filtering the output. Obviously they're very large because it's a bass driver, a couple of drivers, a relay, which may be just to protect the output, I'm not sure, and then a big heatsink, and then this section is power supply, universal power supply, very large, big, obviously switching transformer, some big transistors mounted down here on the heatsink. I can see 3 large devices, presumably 4 large devices, presumably a rectifier, 2 outputs and a thermistor, another relay, 2 large smoothing capacitors for the power supply. It's universal input, so somewhere there's got to be a bridging circuit to actually switch this from 110 input to 220. So it will double on the 110. It will double the mains input voltage driven onto these 2 capacitors, which are probably in series. We'll find out. Some black stuff on here. Look, is that my thumb? Black sooty powdery stuff has come from somewhere, emanated from within a component, do you think? Haven't quite worked out the purpose of this board. On the back of here, back of this board is mounted the mains input socket. If we just zoom in on that a little bit, you can get a better look. Okay, and so can I point with? It's not been plugged in yet by me, so mains input coming in here, a relay on here. I'm not quite sure why we'd need a relay. If this was a doubler circuit, you would need, I think I'm right in saying you'd need 3 connections, and I don't think the bridge rectifier is on here. We'll know more about that when we get the board out, won't we? So yeah, anyway, what's wrong with it? It says, look, this is what they've written at the repair centre. Someone's looked at it and they've written amp and PSU dead. Chuck it back in the box, give it back to the customer, charge customer fee for looking at it, don't bother repairing it because it's too much trouble, or you don't know what you're doing, or you don't have the circuit diagram. So here's our chance, boys, for you to put these professional repairers to shame. If we can fix this and I get enough information, you might be able to fix yours. So let's get on with it. I'm just going to see if there is a manual or a schematic online for this thing. If there isn't, we'll have to work it out for ourselves. So the engineer repair Johnny looked at this, said it couldn't be fixed, or said it was amp and PSU dead. So I have no idea whether the amp or the PSU, or the amp and the PSU is dead, but something is dead. It's not working. I've tried plugging it in, no light. So I'm just going to take this apart, take the power supply off, remove these screws on this fascia here, unplug her. Right, there she is. I have to say I'm not keen on this bloody stuff. Let's wipe it off. It's like dog shit. It's on the path 1 minute and then it's on half the rugs in the county within the next half an hour. It just spreads. Titanium dioxide, same pigment as they use in white paint. Got tons of this stuff, so I'll just stick some more on. Talking of more on, what if the engineer that condemned this will ever get to watch this being repaired? We'll never know, will we? I do know there's a lot of these guys that are around though. Woke up one day, thought they were an engineer. My dad used to say, "Oh, I think you're an engineer. Wouldn't know his arse from a hole in the ground." That's what he used to say. I never really understood that until I was older. Anyway, let's take my garden hat off. What have we got? Oh dear. Alright, so just looking over this thing. I don't think we can get any closer than that, can we? Or can we? Oh, we can. So we've got the usual thing. Input, filtering, more filtering. Common mode rejection choke, some class Y capacitors going to the ground point in the middle, varistor to prevent surge inputs, mains voltage surges even from the mains, another filter and a relay. So they love their relays, and what they normally do on these amps is have a PTC, positive temperature quotient thermistor, which is in circuit until the secondary voltage powers up and then closes the relay, and then if the power supply fails or whatever, you turn it on, the PTC just gets very hot very quick, goes effectively open circuit, and because the secondary voltage never comes up, this relay never closes. So I suspect that's the relay just to short out the PTC, or it's a voltage doubling relay to bump up the 110 to 220. Now this, when these relays contacts close, there's quite a jolt in current if these capacitors are charged up already. Look, see, it's all over my fingers already. Bloody stuff. And often these relays get welded shut, if that is the one I'm thinking. I don't know whether it is, I've never seen this before, but we'll work that out. But if it is a 110 to 220 volt relay, then we're just going to take that out. And so if you're only running on 220 and you see this doubler relay and the universal input JBL stuff, you don't want that relay in there. You want to get rid of it, because when it closes, often enough to cause you a big problem, the contacts get shut. It gets welded shut. So you would consider that a major reliability issue actually on the other designs. I can't really speak for this. Now I do notice something about this. Is the first thing I notice is, look, I don't know how much this speaker costs, but look, they've used and I don't think I've ever seen this in a main switch mode power supply, but they've used, can you see that down there, 85? They're actually 85 degree capacitors stuck together with silicone, and there's samyon, God knows what they are, samyon, some old crap. So it could be, what I haven't managed to spot on this yet at the moment is a mains fuse actually. Can you see it anywhere? I can't see a mains fuse. Live and neutral come in there, so the mains fuse must be in the socket in the back of the unit, which I think it is on JBL's, come think of it. So here it is, and the mains fuse is in the back. There's the on-off switch. Okay, it feels okay. There's the mains fuse. 5 amp. Yeah, that looks alright. 5 amp mains fuse and an on-off switch that feels okay. Let's have a look to make sure the switch is good. We don't like bad switches, do we? Right, so if I just probe onto these two, which is the other side of the main switch. Right, let's just check the mains fuse. I've got my finger underneath. I can switch up backwards and forwards. So by fingering around the rear, I can make this actuate. If I can get hold of both of these at the same time, we'll be in business. So we're getting 3 ohms, 2 ohms. So yeah, main switch is good anyway, so that's not going to be a problem. Sometimes they go intermittent or slightly open circuit, you know, 50 ohms, 30 ohms, where it's all crusted up the contacts with oxide as it's arced, and yeah, they don't work very well. So what's on this board then? Anybody any ideas what this input board we've got? That's interesting. Yeah, so here we've got, what have we got? A relay. Now bear in mind that this can't have the voltage doubler switching point because there'd have to be 3 wires from here. At the moment there's just live and neutral going into the power supply board here via these 2 connections, look. And there's no center tap point for a voltage doubler, so the voltage doubler must be on here, controlled by this relay, I think. We're going to have to reverse engineer that, the control by this relay. Yeah, curious. The way I understand it, if there was a voltage doubler on this board to double voltage across these capacitors for the B plus when you're running 110, then you'd need 3 wires. You'd need one to go to the center point or AC 0 volts to come back to the point on the bridge rectifier. The bridge rectifier is here under there. You can see there's the 4 connections to it. That's the Ptc thermistor in there. So this relay switches out that PTC, and it's quite interesting actually. It does stick those contacts sometimes. And they've used a much bigger relay on this. Maybe because they had the experience with the 515 XDs and the 315s of the actual doubler relay getting welded shut, so that then when you put the power on at 220 you ended up getting twice the voltage across the capacitors as you should. And mentioning that, these are, as I said, 85 volt degree capacitors with some stuff in between, but look at this. If I put it down like that, you can see that. Can you see that? This one's flat and this one's got a bit of a dome on her. Can you see that? I'll try and zoom in so you can get a better look. So flat top, domey top. Now I'm wondering whether this one's put on a bit of a bulge for us. What do you think? Should we have a look? If I can find a knife, I can take her end cap off. In order to repair this, if this capacitor does prove to be okay, we can put some Kapton on it, can't we? Yes, we can. Kapton. Nice tungsten blade. If you ever buy these, what we call in the UK Stanley knife or craft knives, for 30 quid you can get a big pack of about 50 tungsten blades, and they last literally 10 times as long as the ordinary steel ones. They're very, very sharp and very long lasting. I bought one pack maybe 10 years ago and I still haven't used them all, and I do a fair amount of craft work and stuff. They're just so sharp. Here, look. Definitely she's got a bulge on compared to this one. So we may have had a slight boil up in this, an event that's boiled up the inside of that cap. Bear in mind they are Samyong. Samyong, anyone heard of Samyong? And of course this was made in China, so you know, in China if you order Samyong capacitors, the only way you can make sure they're Samyong is to go to the Samyong factory and check they're not lying to you. and then pick up your capacitors. So as soon as they go into the supply chain, anything can be substituted for anything. There is no holds barred when it comes to substitution of caps. We just slice these down the middle and then we should be able to get them out. So I'm thinking those caps are gone at the moment, so the first thing to do is, you can see they're cemented on the board. Bear in mind this is a bass amplifier. This thing's going to be shake, rattling, rolling, and it's another soft material. If you ship these caps in a monitor or a power supply on a ship next to the engine room with a propeller throbbing for 6 weeks, you'll have a bag of nuts and bolts when you get back. And in particular on these caps, they rock backwards and forwards on their legs. Ooh, hello. And yeah, you end up with kind of stress fractures and bits inside becoming disconnected that shouldn't be disconnected. So I'm going to take this one out anyway, because it's not looking healthy, is it? Let's face it, it's not looking good for it. So let's just whip her out and have a look at it, shall we? This is going to turn out to be a really boring repair. It's an interesting product, but if it's just a simple repair, it's going to be fairly boring actually. I'm rocking and rolling underneath. My fingers are doing behind the scenes, my fingers are working away. Still feels a bit tight, so it's stuck on the board there though. It's coming, she's coming. Yeah, we just need to give it a bit more force, I think. You have to be a bit careful when you're rocking from side to side, because if you put all the pressure on one pin, you will damage the capacitor or lift the track off the board. You know, when I was a younger man, if you were working on a board with capacitors over 50 volts, you had to wear safety specs, because the older electrolytics especially would explode, and sometimes the tantalums especially, if the old tantalum capacitors, which were widely used on logic boards to decouple the supply rails, if they were reversed in manufacturing, you turned it on, they would get hot and they would explode with a hell of a crack, and if the debris happened to go your way towards your eyes, you could have been in trouble actually in those days. So they've both been rock and rolled out of position. So what are these caps doing for us? Anything or nothing? So no sign of bulging on this one, which has got the bulging on the top. Look, you see it's bulged on top when we slice the top off. There's no sign of bulging in the rubber seal in the bottom, which is interesting. So these are supposed to be 680 microfarad, 200 volt. So for the first thing I would say is, on a voltage doubling power supply, 200 volts is way too low. I mean, normally on usual 230 volt mains, there'll be 160 across one of these, and if you go up to 268 volts like I've got my house, this will be over voltage. So yeah, wrong capacitors really. Bad spec. 85 degrees should be 105, should be 250 volt working, not 200. The question is, will anything bigger actually fit in? And just see what they are, see what the old capacitance meter tells us they're doing for us. Anything at all, it might be okay actually, in which case we're going to look a bit stupid, but you never know. So which one's negative? That side. So that's 547. So that's down on what it's supposed to be. It's supposed to be 680, but it could be minus 20. So 547. Oh, I don't know. Anyway, 543. It's pretty low. And this one. $612. Both of them are down on the luck. The Domi one is 543. So what is that in terms of percentage shift? 680 minus 543 divided by 680. So that's 20% down. So that could, in theory, just about be in spec if this is a plus minus 20% capacitor. But they're nasty, aren't they? Samsung capacitors any good? SAMXON capacitors. Good. Yeah, it says Samsung. Panasonic is very good, which I know, and it says here on the EV blog, Samsung series are problematic as we see a lot of them at badcaps.net. So I didn't know there's a website called badcaps.net. Trouble is, you don't know who's got an axe to grind on these websites, do you, and what they put. But they need changing for goodness. I don't know what the DC leakage current is because we can't measure it. I've got a box for doing that. Let me just put it on the box and see what it comes back with. Just to orient you, there's the bridge rectifier for the mains. There's one trench stop FET or a FET. There's the other FET power. There's the 470 ohms in the gate driving. See, well, 470 ohms in the gate driving. See, that's blown. 100k, 10k will still be all right. Comes back down here to some kind of is that a transformer? Is it a drive transformer? There. So there's the coupling transformer between the drive side and the FET side. So it's an isolated FET drive circuit, and you can see. So 2 transformers in that package. 1, 2, 1, 2. Yeah, so it must be an anti-phase drive circuit, mustn't it? Anyway, so these are driving into this, and this drives into there to actually switch the FETs. Yeah, you do see that on very high power supplies, switch mode actually. I'm not sure. I think it's to do with ground impedance in the board. It's to stop. If there are any resistance, you've got very high currents going, to stop the potential developed across the AC 0 volt rail and the signal circuits. Clearly the high side of this will be need to be isolated relative to the voltage, because these FETs are the same N channel or NPN trench stop power FETs, and you need some drive. So they've chosen to isolate the drive of the transformer rather than using a half bridge driver IC. Okay, so they've cut one. Normally there's a semiconductor device which generates the gate drive voltage from the high side on the flyback, and there's some kind of opto-isolator inside the device. It's got a half bridge gate drive like the MX or the 7380 or 7384 MX chips, but this one they've used these two. I'm guessing they are complementary drive pairs boosting the output from this management chip to drive the input windings of this to get the anti-phase drive. Obviously with this only one has to be on at a time, because all the power for this, I believe this is a quasi-resonant half bridge drive power transformer or switching transformer, so most of the power, if not all of it, will go through this cap. Probably. Is that in series with the windings? Yeah, that's the common part. That's the common line connecting the two bridges, the two transistors together. So this point there is wanged up and down between AC 0 volts and halfway and the half AC volts, or V bulk, and it's fed into there. So all the actual power is going through, believe it or not, the 500 watts or whatever power is going through that capacitor. So that has to be a fairly fruity, a fairly special capacitor. So we've got to, even if we fix everything else, we've got to check that cap to make sure that it's a self-healing, fail open capacitor. And if it's, look at the other videos, you can see them where we've taken them apart, and you can see where it's been tracking inside and healing itself into small areas of silver coating or aluminium vacuum plated mylar or polyester, and you can see the little hairline cracks where it's been healing itself into oblivion. And some of these they work themselves into a low capacitance in case you can't drive the power through. I think I'm right in saying that's the case. I've never seen one of these before. It might be a good point to actually look for the circuit diagram, because no point. Yeah, it is. Yeah, I'm right. Idiots, I am right. I am right for a change. So what is a S6? Let me look up this this chip down here, this little fella. Yeah, that's just I'll put the data sheet up. You can see it's just a PWM management chip with some special features on it, and it's got things like discharge of the caps and slow start. And I'm guaranteeing that JBL don't bother with soft start, because I've already modified the 515 XT with the soft start, because they kept blowing up on startup as They also acknowledge in the technical fault finding document that they blow up on startup, and I know why. But yeah, it's just a power supply management chip. So the question is, we know these FETs are blown in here. We don't know whether someone has swapped, you know, a favourite trick of a lot of repair centres is they have a basket case on the shelf, and then you send your amp in, and you think, oh, hold on a minute, this one's got a good amp in it, and the power supply is blown. So let's put the amp back in the case with this power supply, and we end up with one working unit and a customer with a, where we say amp and PSU dead. I mean, I'd be very surprised if the amplifier and the power supply is dead. If that amp is faulty, I'd be surprised. I think it's just a power supply fault in the wonderfully designed JBL power supplies, not. So I'm grateful for the chap that contacted me, because looks like another stream of revenue for me. More work, but hey, what can you say? Right, okay, so let's, with further ado, let's whip these bloody transistors. I'll take these transistors out. It's going to remove this heatsink from the back, have everything floating in the breeze, and see what we've got when we've taken it off. I like the feel of these screws. They seem to be very strange. Either they're not Ptc drive or they're not Phillips or something. Don't like the feel of these screws at all, to be honest. They are a weird screw head. The bit that I managed to get them out with has got marked with OWIM TS6. So it's a strange Phillips head, maybe. It's not a JS one, not Japanese, I'm not sure what it is, but it's the one that fits these screws best. I know it's intended to, but the Phillips and the normal Ptc drive just doesn't fit them. It might be easier, actually, looking at it, taking the screws out the bottom of the board, mightn't it? But it's kind of academic anyway, because, and why is it academic? Because we've got to unbolt the actual transistors anyway, which are these screws. You notice that the transistors are in a silicon sock, which is a requirement usually. So not a double insulated package, then you put them in a silicon sock. And what would you expect the efficiency of this power supply to be, anyone? 500 watts, half bridge, quasi-resonant power supply, correctly designed, without power factor correction, which is not good actually. If this is an industrial piece of kit, you need power factor correction on here, because the power factor on this, when it's pulling 500 watts, would be truly atrocious. The effects on the waveform of the mains in terms of harmonic distortion. But a properly designed one of these, you could get up to 94–96% efficiency, but I can guarantee you this one is nothing like that. I can guarantee it. So that's the heatsink off, or we want to call it bracket. Heatsinky brackety thing. And what are these devices? Look at the size of these Johnnies. Maybe these guys are right. Maybe these components are so expensive that it's just no one wants to bother to replace them. So I take their little socks off. There they are. There you are. What are you? You're a IRF, International Rectifier. They're good uns. IRFP 460s. Right, so here we've got on these things, these will be going, I'm going to change those as well because I just don't trust them. I hope this transformer's not burnt out though. The secondary windings look mighty meaty. Obviously there's a few turns of very low impedance copper, so hopefully they didn't get destroyed during the event. Should we call it the event? So we've got 2Ls and G1. So what are they? Obviously PNP, NPN complementary pair. The KSA range and the 198 and the other one would probably work okay in this, but to be on the safe side, due diligence to the owner, we better look these up, haven't we? Ah, the parts have arrived. Not all from our radio spares, I've transferred them into a box. Let's have a look, see what we got. We have resistors, there they are, 47 ohm, 3/4 watt, 1%, 2010s. One of those is blown up, isn't it, for sure, we saw that. What have we got? Transistors for the push-pull drive for the transformer side, high voltage 150 volt transistors. PNP should be, and if I ordered the right ones, that is. PNP, PPP. Don't tell, is it? That one's PNP, and that one just says bipolar transistor. So I haven't labelled them correctly, but I think I've ordered the right ones, don't you? Then we've got, oh, look at these, individually packed. This is how good these caps are compared to those crap ones that are in there. These are Nichicons. Lovely Nichicons. I can't remember the last time I've seen a blown up Nichicon. And you can see they're the same size and shape of these things, but they are 10 times the capacitor that this thing will ever be. So yeah, a couple of Nichicon capacitors will put the world to rights there. It's one of those in the plastic box. Is there another one? Yeah, we've got 2 of those. So there's the part number I ordered from RS. About £3 each, I think. Quite expensive. Oh, they're nothing to do with this project. There's the chip. Management chip 7147856. That's the power supply PWM management chip. Guaranteed with no soft start on the JBL. It's on the chip, they just haven't implemented it. There's another transistor. Don't know why I ordered that. I've got itchy purchasing finger, and there's the big old FETs in the plastic package. The IRF 460 BPFP or BEs or BFs, doesn't make a difference. 7879140. So that's those 2. So we got all the bits we need to stick it back together. So let's quickly do that and see if you'll play ball for us, shall we? Good idea. Okay, let's just whip these transistors out. Some heat in there. Big tracks. It's going to require a little bit of heat. Bit of smoke. What's that one? The lovely leaded solder to make a lower melting point alloy of the unleaded and the leaded. Just makes it a bit easier to desolder them. There you go. So those shorting links have been removed. And also it occurred to me that 2 things actually. That normally I'm used to changing these complementary drive pair, which boosts the signal from the anti-phase signals from here to drive the half bridge output FETs or transistors. But on this case, it's usually when this device destroys itself, you get the B+ voltage, a high voltage, a full charge full of caps from the caps, a full charge from the caps down through the gate drive circuit, through this 470 ohm resistor on this case. And we look, there's a scar on this one, and we know that one's open circuit because we've checked it. So just to be on the safe side, I'm going to change both of these 470s. These will be fine. So the chances are that this is okay, unless somehow when this shorted it induced a very high voltage spike in the primary. The ratio of this is going to be something like 1 to 1 or 2 to 1 or something like that. So it could have fried these transistors and this device. So I'm kind of half-minded to leave the transistors out, power the unit up and see whether this is running and see whether these drive signals are getting through and these transistor signals look okay. It's going to save having to change those, okay? And I'm not quite sure what to do really, because normally I would just get on and change it, but it might save you having to buy the components. So let's have a quick look at this. We'll power it up and we'll get on with it. And I've worked out what this why. If you recall, at the outset of this video I was wondering what this board did, because I couldn't see enough wires going from here into the power supply to actually actuate the voltage doubling circuit, if it indeed was the voltage doubling relay. Well, it turns out, yes, it is a voltage doubling. It's a sensor and a relay drive, and if there's less than 170 volts or something, it assumes it's single 110 volt supply, and then switches in the doubler. But what I didn't realise was that the previous engineers had this apart as actually neglected to put a cable back, and that's the cable for the doubling connections to actually double the voltage on the big two large capacitors we changed. So the doubler circuit is on here. So before I send this back, I was going to remove this relay if I can get this out of here. Yes, I can, because it's the bolts are on this side. So I'm going to remove that and take that relay out, so the customers confirm that they don't want it to run on 110. This is a reliability issue, so we're going to take the relay out so it can't switch in the doubler. It will now be a 230 volt AC only unit. All right, so that's that. They left the cable out, so not only did they snip the cables off, they actually neglected to put some cables back, which is lovely, isn't it? Very respectful of your customer. All right, okay, let's take these. Let's change this here resistor. We can see you can see it's got a scar on this resistor. You can actually, I could tell that was blown even before I measured it because of the scar. It's got cracking on the top and see some tracking, and it's had a hot supper. So let's just quickly change that resistor. Okay, so that's that one done. That was changed for this part, which I've shown you already, but you can have another look. 47 ohm, 1%, 0.75 watt, 2010 thick film, metal film resistor, and the Farnell code is 2324419. And while we're at it, let's get the mother sucker and suck these holes out before you actuate your sucking mechanism. There we are. Good old Weller soldering iron providing the oomph to do this job. Okay, so a quick clean. Yeah, more out of curiosity than anything else. It's nice and clean now. So I'm going to say, yeah, more out of curiosity than anything else, I'm going to fire this board up and see what drive signals we've got, and just curious to see as to whether these have been blown up via the transformer, because any transients will have to come back down through this way and blow up the chip. So we can see if the bootstrap supply is working, and we've got basic drive signals there before we put the beastly transistors back in and start really testing it. Okay, so this is a kind of a health running check. Also, I don't mind changing these, so I bought them already, but I'll put them in stock. But if they don't need changing, it could save you a step. Alright, so I'm just going to go, in the interests of simplifying your repair if you're doing it, I'm going to fire this up. Yeah, I've discovered why this cap is domed up like that. It's a design fault on this board. A design fault. You're okay running on 110 with the voltage doubler switched in like this. Basically this is emulating the voltage doubling, so I'm running on 110 at the moment. But when you run on 220, which point are we looking at? Yeah, on 220 basically what happens is the neutral rail is connected to the 0 volts on here, which turns the bridge rectifier into a voltage doubler. So you get a half wave voltage doubling circuit with these two smoothing capacitors, one at each end. So you get a split rail with a center point, but the center point is only between the two capacitors. Got something to draw on. Yeah, so what have you got? You've got the AC mains coming in to the unit. Basically you've got a bridge rectifier here with AC going in there and AC going into that point. The positive point goes off to one of the 680s down to a center point, and then the other one is connected the same way around, positive there, negative down there, down to here, to this point. Okay. Yeah, that's basically the connection. So you end up with a half wave split rail supply with this somewhere in the middle. Notice there's no DC path in here. So it's just an AC circuit, there's no DC path. So if the leakage current on either of these capacitors is wrong, then I've explained this in another video, this center point should be within, the voltage across each cap should be within a few volts of each other. And if the leakage current on one of the caps goes out of whack, i.e. it starts to conduct more, it will push the voltage up on the other one. Okay, so what most designers do is just put a simple, something like an 82K in there. Around about 82K usually. And the idea of that is to provide a balancing. So if the voltages start to creep out, there is some leakage current going through the capacitor. Every capacitor has got a parasitic leakage current, which is basically if you can imagine it as being a resistor inside the unit. Okay, it's not supposed to be there. Perfect capacitor wouldn't have one, but you know, these aren't perfect. Okay, so you can imagine this parasitic resistance representing the leakage current, I leakage, going down through the capacitor. Now if one capacitor has got a higher leakage current than the other, it can start to change the actual voltage. Their midpoint voltage can drift, especially if you've got some sort of other DC current supply drawing off this. It will take them a long way out of whack. Okay, so what you have is this 82K resistors, as I mentioned, and they're supposed to be an order of magnitude at least. The current going down here is supposed to be an order of magnitude at least of the current that's leaking inside the capacitor. You can see, so then these 82K become by far the most dominant factor in determining this midpoint voltage, and because the current coming down here is much higher than this, they are the dominant factor. So these two resistors will regulate this voltage until the leakage, say the capacitor starts to fail and the leakage current increases, then one or the other capacitors will start to be voltage will climb and eventually over voltage. Now that's fine, okay, and this setup here isn't really important, because on a 110 volt operation, this line here is connected to that line there via that loom that's missing to the relay in the power in the voltage detector board. So on a 110 volts, there's a link in there, okay, in which case this center point voltage is arrested by one of the supply lines. Remember, this is the neutral live supply line there. So yeah, on 100, but on 240, if there's any imbalance on this circuit, especially in DC, these voltages will drift out a long way down. Now I've just turned the unit on and found that these voltages, I always check this voltage whenever I turn something on. I'll put it on the lower voltage on the variac via the isolation transformer, and then we check the voltage to make sure they're more or less the same. You know, they should be within 4 or 5 volts or even a couple of volts of each other on a good circuit. And if they're not in whack, then when you turn the power up to full voltage, you end up one might drift above its voltage rating and damage the capacitor. All right, so always check them, because it will be a source of grief if you don't actually make sure these capacitors aren't leaking or there's not something else pulling the voltage around. So that should be V. That'll be half V, V, and then 0 volts. Okay, we'll call that AC 0 volts. Alright, but on this circuit, I've been looking at this because I thought, well, why is it out of whack? And it's not the capacitor because they're brand new, unless I bought a faulty capacitor, but never happened with Nichicon before. And looking, poking around the circuit, what they've done is on, this is AC 0 volts, so this is also the DC 0 volts, the electronics, okay, for the high side power supply electronics, things like the PWM management chip, for example, and all that electronics will run off that as the reference voltage line, the 0 volt line. And what they've done is they've taken a feed off here down through a resistor. What value is that resistor? Actually, it doesn't go down through a resistor, it goes down through a small resistor to a transistor. There's a Darlington pair of transistors here. There's some other caps and stuff like that, and this has got an 11 volt reference. So this, mind you, this is at naught, this is at half E, okay, DC. And they've actually taken the startup supply from the halfway line down to here, and this goes off to feed your chip. Okay, there's your chip there. There's your PWM. Right. So they've taken this off this circuit, and the idea is that when the power supply starts up, the bootstrap comes along, and then there's a diode here in the bootstrap, goes along to that point, and then when the transformer starts up, there's a switch mode power supply rectifier, small separate stage, which produces via regulation and other things 12 volts. Okay, but that diode is not problematic to us, and this will probably work because when the power supply starts up, it should turn these transistors off, and then what you'll have is just the bootstrap supply running from its own switch mode power supply, supplying the power to the PWM chip and the circuitry, the associated circuitries around here. But what the trouble is, and I understand what happens, if this chip fails to power up, say the power supply doesn't start, or a capacitor or a component blows in here, or there's a thermal fuse as well, there's supposed to be, I think someone mentioned, then this is turned off, and this is permanently drawing DC current down this route here. And on 120 volt AC setting, 110, 120 is not a problem, but without this link, this starts to pull this voltage down, and within 5 seconds of turning on, this is then over voltage. This capacitor is going over voltage, and this is sinking down to 30 volts. So that's why that capacitor blew up, because the power supply stopped working. This was permanently enabled, so the PWM was currently constantly draining through this 82k resistor and the leakage resistance of this capacitor, and then pulling this voltage down, 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 down. So instead of that being DC half of VB up there, instead of being half, this was 30 volts, and this is going to be like 280 or something like that. And you know, that's why your capacitor's fried, basically. So that's the reason for the caps going, and it's a design fault that will only affect 220 volt operation. So what I'm going to do is I'm going to debug this. I'm going to switch to 110, put the doubler link in, put this link in, and now I'm going to finish assembling and debugging the actual power supply to make it work, and then I'm going to look at this and see if this needs fixing or not. You know, if you took it from, you should take it from this point, in which case you're going to need a much higher voltage transistor for a start, so more expensive components. Or take it from this point. Actually, the transistor is acting as a resistor, you know, basically emitter follower circuit. So the resistance, or the effective resistance for the transistor at the bias point, will be acting as a large resistor between this line and this line to get the necessary current to flow down into the PWM chip to start it up. Now this link should only be active for half a second until the PWM starts and the bootstrap takes over and switches this transistor off. But in a static situation, i.e. you're debugging, you have to be careful of that, because if you plug this into UK mains, these capacitors will get fried again, and you'll have all sorts of horrible things going on. So a design fault we need to look at later. So let's put the transistors back in and fire it up on 110 and see what we get. Yeah, so 15 is the voltage in, that's the supply voltage for this chip down here. Comes in through to this transistor, the or does it? Yeah, it goes to the collector of that transistor, which must be a PNP switching transistor. And there's a Xeno diode and a package over here on this side of the board, which I think the collector of that PNP transistor goes to. So it goes to this supply here. So this is just an ordinary rectifier supply with a dropping resistor to give the startup voltage down to here, which is then switched in through some control circuitry somehow by this transistor to apply the DC power to the device. So if we just turn that on, right, we're working on 110, so I'm just turning the power on, so we've got power on now. Yeah, the power is on, so onto our 0 volt point. Bearing in mind there's 160 volts across those two, so I don't want to touch those. and see what we've got going into the transistor, which is this track here, this track that goes down to here onto the collector of that PNP switching transistor. So we've got 15 volts on there at the moment, 15.4, and what have we got coming out? So onto the DC input voltage for this chip down here, the PWM chip, we have nothing. We've got 59 millivolts on there. So what have we got on the base of this transistor? Naught. So what's on the base of this one? So this transistor is turned on, that's an NPN. That's low. That should be low. That should be low. The collector, sorry, the emitter is high and the collector is low. So that PNP transistor should be turned on, but it's not. So I think that PNP transistor down there is blown, giving us no DC supply on there. So let's whip Q10 off, which is just a PNP switching transistor, and I'll put a new transistor on and we'll try it again. So it'll be one of those, 5450393 from RS. Let's open it up. Okay, so we've had power on this thing. It's turned on at the moment. I'm just going to turn it off, and I'm just going to short the big reservoir capacitors out with I've got a 10 ohm resistor to discharge these caps. There's one, always makes me jump. There's two. Okay, so they're now dead. We haven't got to worry about those. Stick a wee bit of flux on this transistor. It's a big track there. I'm going to put a bit of heat in. There we go. And whilst we're in the vicinity, we can just drop the new one on. There you go. So the new transistor is on. Joints look okay. Put the power on, see if we get any juice this time. So it does, obviously, one obvious conclusion of this is that other components have been damaged during this event, not just the actual output transistors and the capacitors. So let's see what we've got on there now. See if we've got anything on pin. Hey, it's running. Oh no, wait a minute. Wait a doggone minute. Pin 15, be in. 4 volts. Well, we've got something now, but it's not right, is it? It should be more than that. That should be more than 4 volts, boys. I'm pretty sure. What have we got on the reference pin? 2.3. So there's some life in her, but she's not actually fully happy at the moment. There should be about 12 volts on there, I should think, when it's running, and 40 volts when it tries to start. So I wonder what's going on there. Okay, so we're going to change this chip. I just don't think it's worth the risk of blowing the new transistors and everything else by hindsight without changing it, because it is going to be slightly old. It may have had a nasty jolt when the thing went wrong. So for the 60p, or whatever it costs, I'm going to change it. Even if it's slightly part way faulty, it could just go again and then we're back to square one, which would not be good. So I'm doing it like this. I could use more hot air gun, but I thought you'd be interested to see this again, yet again. keep repeating the same old stuff, and then people will get bored eventually, hopefully. No, that's not true. There we go, that's the way we do that. Bit of the old solder mop. Give her a bit of a soak. Suck it all up. There we go. Don't like the look of that bloody track there, do you? Not much. Not much, they say. Don't like that much. Let's cut that off. Carve that little tail because it's leaning over the pad. That's better. I'm liking that more. Right, find the chip. Yeah, I've been investigating this design fault, and I'm more convinced that it is a design fault actually. If I just demonstrate to you what I mean. At the moment I've lifted this component here, which is the startup supply. So the startup, well, when I put the power on, the system won't start up. And there's another resistor underneath which is part of the startup supply, resistor number 6. This one's a big metal film resistor, a wire wound one underneath to take the power. That's removed too. So in theory, when it starts up and it's running, it should be in balance when the switch is off, but it's not, because they seem to have a balancing resistor that I showed you in that diagram across this capacitor, but no balancing resistor across this capacitor. So they've obviously tested this on 110 volt supply and hadn't realized that when you run it on 220 or 240, the voltage goes out of balance, and that's going to do two things. That's will make your switching circuit on the half bridge asymmetric, so one transistor will be taking a lot more current and voltage than the other, and the capacitors are going over voltage. That's why that capacitor is blown up. I just demonstrate to you now. It's not running, but it's in equilibrium. It's the capacitors and the rectifier and all the power input circuitry is turned on. So if I turn it on and make a quick measurement, we can see that at turn on we've got 142 volts on that one and 176, and look at it climbing. Can you see it climbing? And as that one climbs, this is getting up towards its 200 volt limit. This one is declining because it's out of balance, and that one's going down. So you can see that the DC or the direct leakage current or circuitry is imbalancing those caps, and that's why that cap blew up. And there are some components missing. They clearly haven't thought about the design on this. So I'm just going to add a balancing resistor in. I'm going to change these two 104s here. Actually, this one gone over the top now. It's probably gone over its limit, isn't it? Well, it's getting close. Look, that's going to go over 200 in a minute, so I better turn it off. So I'll turn that off and talk to you. So there's 100k, 200k across this one, which is a bit low. Normally the balancing resistor is about 82k, okay? So, and there's none across this side at all. What I've got here is a lashing of lash up of supplying the actual startup current. Because of this circuitry is so, I'd say, unconventional, they've used a chip which isn't really designed to run from a resistive dropper supply. It's too much current. Normal startup chips take a few milliamps. This thing is taking I'll just turn the power on. This is feeding into the output of the dropper and the arrangement with this transistor up here or up there. Let's take the magnet off it. Yeah, there's a transistor here. Look, you can see these transistors and this resistor dropper and this big resistor act as a supply to get the unit running, startup supply. Okay. Now, the trouble with this is it's unbalancing the actual reservoir capacitors in the half bridge when you're on 200 volts, which I've already explained. So I'm just checking this, and I've just connected this up as a lash up. Mains isn't on at the moment, it's just supplying from a low voltage supply, and it's taking, on the power supply I can read 47 milliamps. So it's 11 volts going in, 47 milliamps. So there's 47 milliamps being drawn out the center point of the capacitors, the AC or midpoint, or V mid as they call it, and yeah, it's just unbalancing it. And if this fails to start, the first thing we'll do will be instantly fry one of the mains capacitors. The main spooling capacitors will fry because it will go over voltage, because it's unbalancing the circuit. Now, it is pretty awful actually. I'm sort of getting to the point where I'm not I can think of several ways for fixing it. I'm just thinking about the way of least resistance, i.e. the way to fix it that will make it easy for everyone else to modify theirs. So the problem is, we could take the feed for this transistor here. This transistor is biased to provide 11 volts on the emitter. It's a NPN transistor, and there's a 1.3k resistor, that one in series with the midpoint down to the minus volt rail. So this one regulates from 160 volts down to 12 volts at 47 milliamps. So you can see it's going to get quite hot if it is left running, and also if it's left running it will just unbalance the capacitors. And I wish I'd actually I should have bought this capacitors here. These ones are available in 250 volt. They're 5mm higher, still Nichicon, but they're 250 volts. So if you're fitting them, buying some, then buy the 250s, okay? That will minimize the risk of the failure when the power is off. But when the power is on, it won't minimize the imbalance in the gate drive for the half bridge output stage. So you're going to have an imbalanced, you know, one FET's going to be working much harder than the other basically. And yeah, I'm not sure what happens when it gets under a heavy load, but we'll try that. But I need to get on with this and I haven't got much time. So yeah, it's taking 48 milliamps. This balances up the capacitors in the quiescent state, so that's the correct balancing circuit. What I really need is some 150 volt AC varistors to go across these capacitors, because I haven't seen a half bridge design with a floating center point like this without a varistor on both sides of the capacitors to stop this imbalance. But they won't stop it accurately. They won't stop it swinging too far, because obviously it's 200 volts on one and 120 on the other. That's no good either. But it will protect the devices, the actual capacitors themselves. So it's a shitty circuit. I've never seen anything like it really. It's awful. Yeah, so choices are to fit a small, I know it's gone out of focus, up my head again. Yeah, the choices are to fit a separate offline buck regulator supply to provide this 11 volts, and then that will sort the problem, I'm sure. But I don't have, do I have one? I don't think I've got a circuit board in stock that I could slice up to provide the supply. I'm trying to think if any of my products have got that on. I know someone who has, because I designed one for him. Oh yeah, okay, well anyway, so that's the situation. It's taking too much current. This is a stupid circuit, and I could re-engineer it to take it from the positive volt line, but we'd need a much bigger resistor, and there'd be a lot more power losses in the unit, because we'd be working from the, instead of the midpoint which is being dragged down, we could arrange it to work from the positive supply rail on the B+. But we'd have to drop another 200 volts or 160 volts, so things will heat up more, and that is an issue too. Yeah, suggestions. I can't. I mean, in all confidence, in all conscience, I can't send this back without fixing this problem, really. And it's taken me much longer. I thought it was going to be a straightforward repair. It turns into a complete, well, analysis of why this thing is unreliable, why that capacitor is blown up, and it's very clear. I don't know whether it's an iteration of an old board or you know, an old iteration of the board, older version, but it's just so wrong. I can see actually there is a designer's mark. I don't mind if it's I'm betting it's a stock Chinese power supply they've just bought and slapped in, but either way it's rubbish, crap design, and I'm going to think about it and come back to you. Well, progress on this abomination of a power supply. What I've got here is a lashing of lash up of supplying the actual startup current. Because of this circuitry is so, I'd say, unconventional, they've used a chip which isn't really designed to run from a resistive dropper supply. It's too much current. Normal startup chips take a few milliamps. This thing is taking, I'll just turn the power on. This is feeding into the output of the dropper and the arrangement with this transistor up here or up there. Let's take the magnet off it. Yeah, there's a transistor here. Look, you can see these transistors and this resistor dropper and this big resistor act as a supply to get the unit running, startup supply. Okay. Now, the trouble with this is that it's unbalancing the actual reservoir capacitors in the half bridge when you're on 200 volts, which I've already explained. So I'm just checking this, and I've just connected this up as a lash up. Mains isn't on at the moment, it's just supplying from a low voltage supply. And it's taking, on the power supply, I can read 47 milliamps. So it's 11 volts going in, 47 milliamps. So there's 47 milliamps being drawn out the center point of the capacitors, the AC or midpoint, or V mid as they call it. And yeah, it's just unbalancing it. And if this fails to start, the first thing we'll do will be instantly fry one of the mains capacitors. The main spooling capacitors will fry because it will go over voltage, because it's unbalancing the circuit. Now, it is pretty awful actually. I'm sort of getting to the point where, okay, now it's running at the moment with the 82Ks in instead, and to balance up the grid. There's one of them's been changed. This one's been changed from 200K to 82K to over double the actual balancing current, and this has been added because there is no path for balancing current on the other capacitor. But it's running. We've got output at the moment, and let's check the voltages. It's got 138 on that one. Is it moving? It's reducing slightly, so that one's creeping down. $128. So actually, it's more or less balanced, isn't it? Yeah. So some tit has left the balancing resistors off on the design. Now, to make this reliable, as I said before, we need to put a 150 volt AC varistor. Come on, back to life, you. Yeah, we need to put 150 volt AC varistor, mind their eyes, across both caps actually, to stop this when this power supply it shuts down, and it can shut down because there's a thermal limit switch in the feed to the chip here. There is a connection that goes to a thermal switch. So if the thermal switch goes open because your speaker's got hot in the sun, or you've been driving it very hard, then it turns off the supply to this, and you're back again with the imbalance, and this will drift out and damage the capacitors. And it's exactly what we saw. It's not something wrong with this particular one, it's something wrong with the design. Now, I'm going to get a 150 volt varistor and see what happens. So I'm going to fit it on there somewhere. Yeah, I'm going to get some 150 volt varistors. I don't know if I've got any actually. I might have to order some, which is a shame, because I was hoping to do this before I go on holiday. Introducing the K-Wheats meter HT118A. Haven't reviewed it yet, I'm going to, but it was fairly cheap, but not that cheap actually compared to the DM100C. But yeah, you should be able to read that more easily. Anyway, I'll show you what I've done to do this, to fix this problem, I think. You can see here we've got, these are the big capacitors underneath. Okay, if you can get the 250s, put the 250s in anyway. That'd be a good start rather than 200. They're only 5mm taller, and they're only about 50p more a set. So get the 250s if you can get them. So what I've done is I've taken away the 100k resistors. You can see there's 4 pads under there was 2 100k resistors, and replaced it with an 82k 1 watt resistor. I've put this is not a new varistor, it's from a used piece of equipment, but I haven't got any 150s left. So that's a 150 RMS K150 varistor, which will start conducting about 190 volts. By the time it gets to 210, 220, it'll be conducting enough power to balance this bridge and not over voltage this capacitor if the power supply stops working, i.e. it gets hot and the cutout goes. It won't sit there frying your capacitors. Okay. Now to balance up this drift problem we've been having with the asymmetric drive and these capacitors not charging up to equal voltages, I put another 82k resistor there on the minus side supply. Okay, so that's the midpoint there. So that seems to balance it up, and we'll just try running it now with the new meter so you can see what's going on. That's better, isn't it? I don't know if it works, this meter. I haven't tried it in terms of accuracy, but I'm assuming it's accurate at the moment. So if I turn the power on, no bang, that's good. See what we've got on these capacitors. $142, and that's climbing. It's coming up into balance. Let's just check the AC input. How do we do that function? AC, there we go, 50 Hertz. Voltage a bit low, isn't it? So let's just turn the voltage up a bit. Let's get our 240 of Her Majesty's volts. Yeah, I'm going to have to take my light out of circuit. Hold on. I'll just switch out the safety light bulb. Okay, see how many volts we've got. No bypass now, so this is live mains. AC 217. Uh, 235, that'll do. Okay, so at 235, let's see what we've got on our capacitors now in terms of the DC voltage here. It's not making contact, is it? 159.8. 154.2, so that's close enough. It's close enough jazz. It's within 158.64, so it's coming down slightly. 3, 2, 1. So it's just drifting in. That'll be the capacitors warming up, probably. .55. They're coming into balance, aren't they? 0.6. 157. Still drifting in slightly. Yeah, within a couple of volts of each other on anyway, so yeah, within a few volts of each other, that's fine. And the power supply is running at the moment. We've got plus or minus 40, well 47 actually, 50 volt supply on both sides. Yeah, so yeah, it's working. So that's that done, basically. So that's what I would do if I were you. Stick those resistors in, buy a varistor, put it across that capacitor, and then balance up the two capacitors, and then it'll be much more reliable. It's a horrible design. So I'm going to put this back together now and give it a test. Well, it's all back together and it's working. I was powering it from the other side at the moment, but you can see when I put the power on, the power light comes on. So yeah, it's all fixed. Horrible thing though, really. I don't particularly care for it very much, but that's what you get, I suppose, these days. So anyway, I hope you enjoyed that. If you've got one of those, I advise you to fit the modifications because it will make it more reliable. I'm not surprised it failed. I can see exactly why the capacitors went and why the FETs blew up. But you know, it's a 220 product working on a 110 design with little testing at 220, 240. I think that seems to be the standard with the JBL stuff. Much more reliable on 110. So there's a fix. If you want me to fix any of these 518s, then 518S Eons, then let me know. Subscribe down there in the corner if you could, and leave me a like. I'd appreciate that.